Greetings and welcome to the Quiet Laboratory. I am very pleased you are here. Perhaps your day has been long. Or perhaps you simply enjoy drifting off while contemplating stars, galaxies, and the silent mysteries of the cosmos. In any case, tonight's journey is for you. Nothing is required of you now. Just allow your body to rest, your thoughts to slow, and your focus to gently wander. Because today we are exploring the universe itself. Not a single galaxy or an isolated star, but the entire enormous expanding whole. We will transition smoothly from concept to concept, discussing black holes, ancient light, dark matter, and distant galaxies. Some ideas may surprise you, others may linger nearby, like a quiet thought at the boundary of sleep. And if these peaceful explorations help you to relax, you may consider liking and subscribing. This helps others find their way here. And now, if you are ready, let us begin. The universe may be older than currently estimated. Its age is presently calculated at approximately 13.58 billion years. This figure is primarily derived from measurements of the cosmic microwave background, CMB, and the observed rate of spatial expansion. However, not all methodologies yield consistent results. Certain observations of ancient stars and galaxies suggest they may predate these age estimates. Other studies question the standard accepted expansion rate or propose that dark energy may vary over cosmic time. These discrepancies remain unresolved, and the majority of cosmologists still adhere to the 13.8 billion year figure. Yet, questions persist. Could the universe be older? Have we overlooked a fundamental parameter? Perhaps what we currently define as the beginning is only a segment of a longer, stranger history. The cosmos contains countless rogue planets wandering without stellar hosts. Not all planets orbit suns. Some are completely unbound, drifting solitarily through the galaxy without a star to warm them or illuminate their skies. They may have formed conventionally before being ejected from their systems by gravitational chaos, or they might have originated independently as failed stars, sub-brown dwarfs. They are dark, cold, and nearly invisible, detectable only when they transit distant stars through microlensing or when they emit faintly in the infrared spectrum. Scientists estimate that there could be billions of such worlds within the Milky Way, potentially outnumbering the stars themselves. Each one is a silent planet, drifting in the void, orbiting through the infinite interstitial spaces between stellar bodies. No sunrises, no sunsets, only an eternal night, interrupted solely by distant starlight. The universe might undergo infinite cycles of rebirth. Standard cosmology describes a cosmos that began with the Big Bang and continues to expand, perhaps perpetually. However, some theories propose an alternative history, a sequence of expansions and contractions. In these models, for example, cyclic cosmology, the universe does not conclude its existence in a cold demise or a final collapse. It resets the cycle. Upon reaching a critical threshold, it may contract inward, only to rebound into a subsequent phase of expansion. Each cycle obliterates previous structures, but leaves faint traces of what existed before. These concepts are currently only hypotheses, but they are captivating. They suggest a universe without a true beginning or end, a rhythm stretched across unimaginable eons, a cosmos giving birth to a new iteration repeatedly. The most ancient light we observe originated approximately after the Big Bang. Prior to that epoch, the universe existed as a searing plasma, so dense and hot that photons were almost immediately scattered. However, as the universe expanded and cooled, a crucial transition occurred. Atoms formed, the fog cleared, and light was decoupled. This ancient illumination is the cosmic microwave background radiation, which we can still detect. It represents the oldest direct signal in the universe, not originating from stars or galaxies, but from space itself at the precise moment it became transparent. The photons we detect today have traveled for over 13 billion years, stretching into long, cold microwaves due to cosmic expansion. This light is faint but persistent, a quiet afterglow preserving the memory of the cosmos's first clear moments. Some stars harbor planets composed almost entirely of diamond. In other planetary systems, the underlying chemistry can be dramatically different. If a planet forms with a surplus of carbon under sufficient pressure, the astonishing consequence can be a diamond world. Astronomers have identified at least one such candidate, a dense object orbiting a pulsar, likely the remnant core of a dead star. Based on its mass, density, and inferred composition, it could consist entirely of crystalline carbon, essentially a colossal diamond. It is too hot to sparkle and would not resemble a gem up close. Yet beneath its surface, immense carbon structures could extend for thousands of kilometers. Such planets are rare, but they underscore the vast diversity of the universe. There exist worlds made of rock, of gas, and occasionally of pure crystal. The universe may possess no edge, only infinite curvature. We readily conceptualize a boundary, a location that can be reached. However, space appears to be structured fundamentally differently. Its geometry is determined by its mass-energy content. Current cosmological data suggests that the universe is either infinite in extent, or it is so vast and positively curved that it topologically closes upon itself. If this latter scenario holds true, one could theoretically travel in a straight line and eventually return to the starting point, not by hitting a physical wall, but by traversing the curvature of space, analogous to navigating the Earth's surface. Moving forward, one finds no boundary, only a closed loop. The universe might operate identically, albeit on a vastly grander scale. It is not infinite in the sense of distance, but infinite in the sense of a continuous path. Our sun may once have had a twin, and it might still exist. Some researchers hypothesize that our star did not form in isolation, but alongside a companion, similar to the binary formation process observed in many stellar systems. If this sibling existed, it would have been ejected long ago, its orbit stretched by the gravitational influence of the galaxy. It may still be out there, wandering along its trajectory, now undetectable to us. Some hypotheses link this lost sibling, nicknamed Nemesis, to extinction cycles on Earth, although definitive evidence is lacking. Yet, the idea persists. Perhaps our solitary sun once shared its birth with a silent companion, which has since vanished among the stars. A single drop of neutron star matter would outweigh Mount Everest. Neutron stars are the collapsed cores of once massive stars, the remnants of supernovae. With a diameter of only about 20 kilometers, their mass exceeds that of the Sun. The material within them is so dense that 1 teaspoon would weigh billions of tons. Imagine a single droplet of this substance. It would be heavier than any mountain on Earth. This density defies common experience. Atoms are crushed so severely that electrons and protons merge into neutrons, forming an almost perfect neutron fluid. Neutron stars are objects of extremes, small, dark, heavy, and rapidly spinning. Yet within their silent mass lies the memory of stellar collapse, a state where matter becomes nearly indistinguishable from pure gravity. Light from a single galaxy can reach us from multiple directions. Sometimes light does not travel in a straight line. Where gravity is especially intense, for example near galaxy clusters, space-time itself is warped. This curvature deflects light rays, much like glass changes the path of light. This phenomenon is called gravitational lensing, and one of its strange effects is that we can observe several versions of the same distant galaxy from different angles. They appear as arcs, smears, or even rings. These are not duplicates in space, but duplicates in perception, different paths light took to reach us through distorted space. In rare instances, scientists have even observed the same supernova multiple times as its light arrived via different gravitational routes. A quiet reminder: even light can get lost, delayed, but still find its way home. The very first stars may have shone 1,000,000 times brighter than the sun. They bore little resemblance to modern stars. Born solely of the hydrogen and helium remaining after the Big Bang, these stars, known as Population 3, formed without heavy elements. This made them enormous, hot, and short-lived. Some may have exceeded the sun's mass by hundreds of times. They rapidly consumed their fuel, shining 1,000,000 times brighter than our star, and subsequently exploded within just a few million years. None of them survived into the modern era, but their brief lives transformed the universe. They forged the first heavy elements, ignited the light of galaxies, and set the stage for everything that followed, including us. Their light has vanished, yet their signatures remain in the chemistry of ancient clouds and the quiet structure of the early cosmos. Dark matter passes through your body while you sleep. As you lie still, dark matter silently flows all around you. This is not an invisible fog. It is a form of matter that does not interact with light, neither reflecting, emitting, nor absorbing it. But it possesses mass and is subject to gravity. An enormous halo of dark matter surrounds our galaxy. And as Earth moves through it, trillions of its particles may pass through every square centimeter of your body every second. They do not collide with atoms, nor do they leave traces, yet they exist, ghostly, constant, and essential. Without dark matter, galaxies would not hold together, structures would not have formed, and the universe would be fundamentally different. We still do not know what it is composed of, but one thing is clear: it is a part of your world passing through you silently and continuously, even while you sleep. Some galaxies exhibit luminosity without a single star. In quiet corners of the cosmos, scientists have discovered galaxies that shine but contain almost no stars. These ghostly systems are filled with gas and dark matter but form almost no stars. Perhaps they lost them in gravitational catastrophes. Perhaps they hardly created them at all. Some are nearly invisible and manifest only in specific light spectra, faint blemishes on deep sky surveys. Such galaxies challenge our understanding of cosmic structure formation. If they possess significant dark matter, why are they not building stars? If stars existed, where did they vanish? These quiet, dim systems drift through space like the forgotten remnants of cosmic history, reminding us that not every galaxy is filled with light. Some drift unnoticed and misunderstood. There is a cold spot in the universe that should not exist. In the cosmic microwave background, CMB, radiation, the faint light remaining from the Big Bang, there is a region of the sky that is suspiciously cold. It is not merely slightly cooler, it is significantly colder and far larger than scientists expected. This spot spans hundreds of millions of light years, and its characteristics do not fit the expected randomness of the early universe. Some hypothesize that it is the imprint of a gigantic cosmic void. Others propose something even stranger: a possible trace of our universe colliding with another during the initial moments of inflation. However, no single explanation currently works completely. The cold spot remains one of the quietest and most unsettling mysteries of cosmology. Not a screaming anomaly, but a subtle hint that our universe may not be exactly as it appears. The moon is slowly receding from us. Annually, the Moon moves away from Earth by approximately 3.5 centimeters. This is roughly the same rate at which human fingernails grow. This slow recession has continued since its formation, about 4.5 billion years ago. At that time, it was much closer, and Earth's solar day lasted only a few hours. The cause is tidal friction. The Moon exerts a gravitational pull on the oceans. The Earth rotates underneath them, and a portion of this energy is subtly transferred to the Moon, gradually pushing it into a more distant orbit. This is a quiet, relentless process, imperceptible on the scale of human life, yet evident on the scale of epochs. In the distant future, the Earth and Moon may become tidally locked, forever facing each other with a single side. For now, the Moon simply drifts away gradually, while we rotate beneath its distant, shining light. Binary stars can exchange outer layers, much like dancers making contact during motion. In certain double systems, the two stars orbit so closely that their outer envelopes begin to touch. As they evolve, one star may swell and transfer a portion of its material onto its companion, forming a thin spiral stream. Sometimes the mass transfer occurs quiescently and smoothly. Other times it triggers flares of light, rapid spin-up of rotation, or even complete merging. The physics of such systems is complex, but the imagery is strikingly elegant. Two stars in a tight orbit, close enough to touch and mingle. One may be left as a stripped, luminous core, the other bloated and chemically enriched. Their fates are intertwined. Some of the universe's most exotic objects, certain types of supernovae or binary neutron stars, begin as these quiet, contacting pairs. A reminder that in the cosmos, even stars can share, change, and sometimes unite. The vacuum of space is not genuinely empty. Even in the deepest and darkest regions of the universe, far from any stars and galaxies, space is never completely void. According to quantum physics, what we refer to as a vacuum is a sea of activity. Minute particle-antiparticle pairs flicker into existence and vanish almost instantaneously. These quantum fluctuations occur everywhere and always, generating a subtle background texture of reality. They can influence the movement of particles, change the behavior of fields, and even contribute to the energy of empty space. It is this energy that is linked to dark energy, the mysterious force accelerating the expansion of the universe. Therefore, while picturing deep space as quiet and still, we are only seeing a part of the picture. Beneath this tranquility lies a dance of probabilities, a hidden hum of creation and annihilation, perpetually occurring at the boundary of nothingness. In different regions of space, time can flow differently. We are accustomed to thinking of time as something uniform, flowing equally for everyone. But in reality, time is intimately linked to gravity, motion, and the geometry of space. Where gravity is stronger, near a black hole or a dense cluster of galaxies, time progresses slower than in regions with weak gravity. This is not merely a theory. The effect has been confirmed by experiments, satellites, and atomic clocks. Some cosmologists suggest that time may also differ on larger scales. Perhaps different parts of the universe experience time with a barely noticeable discrepancy due to peculiarities in its early expansion. The idea remains hypothetical, but it opens up strange possibilities. In a cosmos governed by relativity, time is not necessarily absolute. It can stretch, decelerate, and curve, gently following the contours of the space through which it flows. The Milky Way possesses a hidden halo, which is far larger than the visible portion of the galaxy. When we observe an image of the Milky Way, we see a luminous spiral, stars, gas, and dust organized into beautiful arms. But surrounding this familiar structure exists something vast and nearly invisible, the galactic halo. It is a gigantic sphere of tenuous gas and dark matter extending far beyond the boundaries of the visible disk. It encompasses ancient stellar clusters, individual stars, and immense masses of unseen substance. All of this is held together by gravity, shaped by a history of collisions and mergers, and plays a quiet role in the stability of the galaxy. We cannot observe the halo directly, but we know of its existence through the motions of stars and the way light bends when passing through these regions. Thus, the Milky Way is merely the bright heart of something much greater, enveloped by invisible embraces. We have detected light from a galaxy that originated just 200 million years after the Big Bang. The age of the universe is approximately 13.8 billion years. However, light does not travel instantaneously. It traverses expanding space, stretching and decelerating along the way. Therefore, we observe distant galaxies as they were long ago. Recently, astronomers utilizing the James Webb Space Telescope detected the light of a galaxy that existed only 200 million years after the Big Bang, literally an instant on a cosmic timescale. This light traveled to us for over 13.5 billion years. The galaxy itself is small, faint, and primitive, yet it holds clues regarding the formation of the first structures. To observe it is to gaze through a tiny window into a world we were not meant to see, witnessing the universe in its earliest chapters when darkness was only beginning to yield to stars. The large-scale structure of the universe resembles a neural network. When astronomers map the distribution of galaxies across immense distances, an unexpected pattern emerges. Galaxies do not cluster chaotically. They align themselves along filamentary structures separated by colossal voids. This network, spanning billions of light years, is called the cosmic web. What is particularly remarkable is that if one zooms out sufficiently, its structure bears a striking resemblance to a neural network, such as those found in the human brain. The dense nodes of galaxies resemble neurons, and the elongated filaments resemble axons. Naturally, this is only a superficial similarity. The universe does not possess cognition, but the comparison itself is astonishing. The most colossal structure known to us and the structure within our own minds, created by disparate physics, turn out to be so similar. Stars can sing through the vacuum of space. There is no air in space, and thus we do not hear sound as we do on Earth. Nevertheless, stars still generate sounds, deep, slow oscillations propagating through their internal layers, much like seismic waves within a planet. These waves cause the star to pulsate and oscillate, and scientists detect them by measuring minute variations in brightness or surface movements. This field of study is called astroseismology, literally meaning stellar seismic analysis. Every star possesses its own intrinsic frequencies, much like a unique acoustic signature, which depends on its size, internal structure, and age. By monitoring these vibrations, scientists can probe the stellar interior and determine the processes occurring beneath the surface. This technique functions as a form of cosmic echolocation, a method to hear the music of the stars across light years, even though this stellar song remains silent to the human ear. Some stars are older than the galaxies they inhabit. Galaxies do not emerge instantaneously. They form gradually, accreting smaller systems and drawing in stars from other regions. This implies that a portion of the stars within a galaxy can predate the galaxy itself as a coherent structure. They originated in ancient, smaller galaxies that subsequently merged with the larger one. Such stars are typically found in the outskirts or within globular clusters, dense stellar groupings orbiting far from the galactic center. Some of these are over 13 billion years old, nearly as ancient as the universe itself. They carry the chemical fingerprint of the early epoch, when elemental compositions were far simpler. These stars serve as cosmic fossils, silent witnesses to the era before the galaxy fully achieved its current morphology. Their light is primordial, and their histories commenced prior to almost everything we currently comprehend. There exist galaxies devoid of dark matter, and the reason for this remains unknown. Dark matter is the invisible substance hypothesized to gravitationally bind galaxies together. It accounts for why peripheral stars orbit faster than expected and why galaxies aggregate into clusters. However, in recent years, astronomers have identified galaxies that violate this established paradigm, galaxies that behave as if they contain no dark matter. Their stars move as though only visible baryonic matter is present. This discovery was unexpected and presents difficulties for current cosmological models. Perhaps the dark matter was stripped away during galactic collisions, or perhaps our understanding of dark matter itself is incomplete. Regardless, these anomalous galaxies demonstrate that the universe still holds profound mysteries, and what appears to be a universal rule sometimes proves to be less than ubiquitous. The sun resonates like a massive, reverberating bell. Deep within the solar interior, acoustic waves propagate through the plasma, reflecting off various layers and causing the entire star to subtly vibrate. These waves are unlike conventional sound. They are low-frequency, slow-moving pressure oscillations undetectable by the human ear. However, sensitive instruments record them, aiding in the study of the sun's internal structure. This discipline is termed helioseismology. By analyzing these oscillations, scientists can visualize subsurface phenomena, such as density distribution, the rotation rate of different layers, and the movement of hot gas convection currents. In this sense, the sun is a complex, perpetually sounding musical instrument. One only needs the correct instrumentation to perceive it, and this quiet music helps us understand not only the sun, but stars across the cosmos. Galaxies trace filaments composed of matter we cannot directly observe. The largest structures in the universe consist not of stars and gas, but of invisible dark matter. Over billions of years, it has formed gigantic filaments, and galaxies emerge and traverse along them, like beads threaded on a string. We cannot view these structures directly, but we infer their existence by observing how galaxies cluster and how light is gravitationally lensed in these regions. These filaments can stretch for hundreds of millions of light years, connecting vast galaxy clusters. Between them lie cosmic voids, nearly immaterial regions. These dark filaments form the hidden scaffold of the visible universe, determining where galaxies are born and where they migrate. Yet, we still do not know the composition of dark matter. This immense, invisible structure silently holds the universe together. Space itself can expand faster than the speed of light. Under normal circumstances, nothing can move through space faster than light, but space itself is not bound by this constraint. In the first moments following the Big Bang, space expanded so rapidly that regions of the universe moved apart faster than light could bridge the distance between them. This is not motion through space, it is the expansion of space. Today, distant galaxies recede not because they are flying through the cosmos, but because the space between us is stretching. If they are sufficiently distant, this stretching accelerates them faster than light, rendering them eternally unobservable. This is not a violation of physics, but a subtle consequence of the behavior of space-time on large scales. The universe is unhurried, it simply and calmly stretches beyond our capacity to catch up. Our solar system moves through the cosmos in a twisted spiral. We typically visualize planets orbiting the sun in smooth, flat ellipses. But if we pull back further, something far more astonishing becomes apparent. The Sun itself is in motion, revolving around the center of the Milky Way at nearly 1,000,000 kilometers per hour. As it traverses the galaxy, the planets follow, not merely orbiting but tracing a spiral path through space. All components together create a helicoidal trajectory, similar to a screw thread or a twisted ribbon. Everything in the universe is in motion: planets, the sun, stars, and the galaxy itself. In space, there is no fixed point, only smooth, endless drift. Even while we sleep, we are tracing slow spirals within a moving galaxy located inside orbits nested one within another. It is a cosmic dance so immense that we never perceive it. Even nothingness possesses a temperature. If one travels far enough away from stars, planets, and galaxies into deep intergalactic space, one encounters what appears to be absolute void. Yet even this vacuum holds a temperature of approximately 2.73 Kelvin, just a few degrees above absolute zero. This is due to the cosmic microwave background, CMB, the residual radiation from the Big Bang, stretched and cooled by billions of years of cosmic expansion. This faint glow permeates all of space. Wherever you are, it is uniformly present. The quiet thermal fingerprint of the early universe, and in the future it will become even colder. Over trillions of years, the temperature will approach absolute zero, yet never reach it, because even in the deepest vacuum, an echo of ancient heat remains. Quantum fluctuations may have shaped the entire universe. On the smallest scales, far smaller than atoms, reality behaves unpredictably. Tiny bursts of energy appear and vanish instantaneously due to the inherent uncertainty of the world's quantum nature. According to many cosmologists, it is these random bursts that may have been magnified during the universe's first moments through inflation. As space expanded at an unimaginable velocity, microscopic fluctuations were stretched to cosmological scales. They became the seeds of structure, locations where matter coalesced, galaxies formed, and stars ignited. In other words, the grand pattern of the cosmos, galaxies, filaments, and voids, may trace back to fleeting events at the smallest possible scales. Everything we observe was born from the shuddering of nothingness. Dying stars can pulsate like a heartbeat for millions of years. Not all stars conclude their lives in an explosion. Some fade more slowly, and in their final stages may rhythmically oscillate, expanding and contracting. These variable stars change their luminosity over time, sometimes strictly and uniformly, repeating like a slow pulse. These oscillations are linked to changes in the outer layers. Gases expand and cool, then compress and heat up. Some stars pulsate every few days, while others do so for months or years. These rhythms have long been utilized for measuring cosmic distances. Their period is correlated with their intrinsic luminosity. And this is a subtle reminder. Even as they die, stars can maintain a rhythm, not for hours, but through a long, slow respiration. Throughout cosmic epochs, Earth has resided inside a gigantic bubble of hot gas. If we could observe beyond the visible spectrum, we would find that the solar system is situated within a vast luminous cavity. This is the local bubble, a region extending hundreds of light years in every direction. It is believed to have been inflated by a series of ancient supernovae, whose shock waves heated and displaced the surrounding gas. We are currently drifting quietly within this rarefied region, surrounded by a shell of hotter gas and dust. This presents no danger and is imperceptible to us, yet the bubble exists. A quiet chamber surrounding us, born from an ancient catastrophe, now forms part of the calm background of our galactic neighborhood. An immense void lies beyond the Great Attractor. The Great Attractor is an enigmatic region of space so massive that entire galaxy clusters, including the Milky Way, are slowly migrating toward it. But behind this colossal concentration of mass lies something even stranger, a region known as the dipole repeller, where space appears unusually vacant. This is not merely an area with fewer galaxies, but a gigantic cosmic void, extending across hundreds of millions of light-years. And surprisingly, its void appears to repel galaxies. Together, the Great Attractor and the Dipole Repeller establish a silent gravitational tug-of-war, shaping the motion of our local cosmos. We are pulled forward by unseen mass and simultaneously pushed away by the void behind us. This serves as a reminder that in space, both the presence and the absence of matter can profoundly influence our trajectory. Neutrinos pass straight through the Earth and through us. Right now, trillions of neutrinos are streaming through your body, yet you remain entirely oblivious. Neutrinos, these incredibly light, neutral particles, are produced in vast quantities within the Sun, in supernovae, and even throughout the early universe. They interact minimally with ordinary matter. They can traverse a planet or your entire body without leaving a trace. Only a handful are detected by instruments located deep underground, where extremely rare collisions provide the opportunity for study. However, the overwhelming majority pass completely unnoticed. These particles are ubiquitous and constant, quietly permeating space and matter. They travel at nearly the speed of light, yet they interact with virtually nothing. The universe is teeming with movement, even when it appears static. The most massive stars can transform into black holes without a subsequent explosion. We are accustomed to visualizing the demise of a massive star as a brilliant supernova event. But for the heaviest among them, the end occurs differently, almost silently. When such a star exhausts its nuclear fuel, its core rapidly collapses and gravity reigns supreme. Even the outer layers fall inward. There is no explosion, no luminosity, only sudden disappearance. This process is termed direct collapse. In an instant, the star vanishes, leaving behind a black hole that is silent, invisible, and incredibly dense. Astronomers have observed stars that simply disappeared, as if their light had been extinguished. This reminds us that not all celestial final acts are fireworks. Sometimes, the finale is merely a whisper into the darkness. Galaxies can orbit one another, much like moons revolve around planets. We often perceive galaxies as isolated cosmic islands, but many exist in groups, actively interacting and even revolving around one another. The Milky Way possesses dozens of satellite galaxies, the best known being the Large and Small Magellanic Clouds. These satellites travel around the Milky Way, similar to moons, tracing long, elliptical orbits. Occasionally, a larger galaxy tidally strips stars from its satellite, creating stellar streams extending millions of light-years in length. Over immense timescales, the smaller galaxy can be completely absorbed. These cosmic dances unfold over billions of years, slow, majestic interactions on unimaginably vast scales. In the silence of space, even galaxies can be neighbors. The brightest explosions in the universe originate from the collapse of highly magnetized stars. There is a rare class of explosions, the magnetar hypernova, which are arguably the most luminous events in the cosmos. A magnetar is a neutron star possessing an unimaginably powerful magnetic field, trillions of times stronger than Earth's. If a collapsing massive star forms a magnetar and releases its energy rapidly enough, it can generate a flare significantly more powerful than a standard supernova. Such events likely trigger certain long gamma-ray bursts, high energy flares that briefly outshine entire galaxies. The explosion lasts only seconds, yet its light can reach us billions of years later. It is one of the most intense phenomena in the cosmos, born from a small, dense object enveloped in magnetic plasma. The edge of the observable universe, not the edge of the universe itself. When we look into space, there is a limit beyond which we cannot see anything, approximately 46 billion light-years distant. This constitutes the edge of the observable universe. It is neither a wall nor a barrier, but simply the maximum distance from which light has had time to reach us since the Big Bang. However, the universe almost certainly continues beyond this point. We simply cannot observe it. And because the expansion of space is accelerating, some regions are receding from us faster than the speed of light. Their light will never reach us, even given infinite time. The observable universe, this bubble of visibility, is only a segment of reality. Beyond its limits lie more galaxies, more stars, perhaps infinitely so. Some galaxies emit jets of plasma spanning millions of light-years. At the center of many galaxies reside supermassive black holes. Sometimes the matter falling into them does not disappear entirely. A portion of it is captured by magnetic fields and expelled outward in narrow, powerful streams of plasma. These jets travel close to the speed of light and can stretch millions of light-years beyond the galaxy itself. We observe them in the radio spectrum, gigantic luminous regions marking their trajectory. Galaxies featuring such jets are termed radio galaxies. Their relativistic jets are among the largest structures in the universe. A strange paradox, the most powerful outflows originate near black holes, locations where light itself can barely escape. Even stillness, it seems, is capable of leaving a trace. There is a star that orbits the Milky Way in the reverse direction. Most stars in our galaxy move in one direction, adhering to the overall rotation, but not all of them. At least one star, H4075-439, acts counter to this. Its orbit is retrograde. It moves against the galactic flow, like a salmon swimming upstream. How did it end up there? Perhaps it was once part of a smaller galaxy that was subsequently absorbed by the Milky Way. Its orbit may preserve the remnants of the former system, or it might have been flung there by a gravitational assist maneuver involving a black hole or a dense cluster. In any event, this is a quiet reminder that even within the immense mechanism of a galaxy, there are wanderers who follow their own trajectory. The galactic center smells of raspberries and rum. It sounds like a joke, but it is factual. Astronomers studying the composition of a molecular cloud near the center of the Milky Way detected a molecule called ethyl formate. On Earth, this compound is associated with the flavor of raspberries and the aroma of rum. Naturally, the galactic center itself does not possess a scent. Vacuum cannot transmit odors. However, the presence of such molecules indicates complex organic chemistry operating in space. Interstellar clouds contain alcohols, sugars, and even precursors to amino acids. This is not life itself, but the chemistry from which it may commence. Thus, while space does not carry the aroma of fruits and spirits, it nonetheless holds the ingredients, silently propagating between the stars. One galaxy is gravitationally bound and heading directly toward the Milky Way, already initiating contact. The Andromeda Galaxy, our nearest massive neighbor, is approaching us. Currently, it is situated approximately 2.5 million light-years distant, but this separation is continuously decreasing. In approximately 4 billion years, the two galaxies will commence their merger. Intriguingly, the outer galactic halos of both systems, their immense envelopes of hot gas and dark matter, are already overlapping. Conceptually, they have already made initial contact. Their ultimate convergence will constitute a gradual coalescence rather than a catastrophic collision. The constituent stars will largely traverse past one another without physical impact. Over time, the two spiral structures will transform into a single massive elliptical galaxy. We occasionally refer to this future resultant system as Milkomeda. Although the wait is protracted, the process is already underway, a cosmic rendezvous spanning billions of years. The cosmic microwave radiation persists, permeating your surroundings. Every region of the universe, including the immediate local space, is saturated with a faint electromagnetic glow known as the cosmic microwave background, CMB. This represents the afterglow or residual radiation from the Big Bang event, specifically the photons released when the universe was approximately 380,000 years old. At that epoch, the cosmos consisted of a tense, dense plasma. As it cooled sufficiently to allow for the formation of neutral atoms, recombination, light decoupled and gained the freedom to propagate. It continues traveling today, stretched into the microwave portion of the spectrum due to the expansion of space. Presently, we detect this radiation as an almost perfectly isotropic glow across all directions. While it remains imperceptible to human senses, highly sensitive instrumentation registers it as a pervasive cosmic murmur. It constitutes the most ancient radiation observable, a subtle signal originating from the early infancy of the universe, still echoing across the expanse of space and time. Certain supernovae are fueled by an invisible core collapse rather than electromagnetic radiation output. Supernovae are renowned for their intense luminosity, cataclysmic explosions that momentarily eclipse the integrated light of entire host galaxies. However, not every core collapse event yields substantial luminosity. Some are classified by astronomers as failed supernovae. In these scenarios, the core of a massive progenitor star collapses, resulting in the formation of a black hole, yet the stellar envelope fails to eject outward in a brilliant outburst. Instead, these outer layers may undergo infall, quietly accreting onto the newly formed black hole. In rare instances, we have observed massive stars that appeared stable, only to vanish abruptly. Absent a visible explosion or a prolonged residual luminosity, only darkness remains. Such disappearances indicate a gravitational collapse so comprehensive that nearly all released energy is instantaneously absorbed. The inherent violence of the event remains immense, yet entirely obscured. This serves as a reminder that not every instance of stellar demise manifests loudly. Some occur in profound silence, deep within a powerful gravitational singularity. Entire galaxies exist that are fundamentally composed of baryonic gas and dark matter, with minimal stellar content. We conventionally visualize galaxies as brilliant spiral formations or luminous elliptical systems saturated with billions of stars. Yet some galaxies are barely detectable. These faint structures contain very few stars, but still possess mass primarily in the form of gas and dark matter. They are challenging to detect using conventional telescopes. They appear only as faint smudges or are revealed through indirect methodologies. Some of these may be failed galaxies, systems that never formed a substantial stellar population. This could be because their gas was stripped away or heated too early in cosmic history. Others might represent transient evolutionary stages of galaxies, but they all share one characteristic: their invisibility. No bursts of light, no spiral arms, just a quiescent gravitational presence. They remind us that not all galaxies shine brightly. Some simply exist. Black holes can collide and merge in cosmic dances. As two black holes orbit one another, they emit ripples in spacetime, gravitational waves. As they lose orbital energy, they spiral inward until they coalesce in a final dramatic moment, and the two invisible giants become one. These collisions do not generate light, but they send out bursts of gravitational waves that we can now detect here on Earth. The first such signal was observed in 2015, confirming Einstein's prediction from a century prior. Since then, we have detected dozens of similar events. Every pulse recounts the history of massive object collisions in distant galaxies. These black hole mergers occur quietly, invisibly, yet with incredible power, converting entire solar masses of energy into waves propagating across the universe, and for a moment, the very fabric of spacetime begins to resonate. Some stars die in slow motion, spending billions of years on their demise. Not every star ends its life in a sudden explosion. Smaller stars, such as our Sun, expire much more gradually. When they exhaust their hydrogen fuel supply, they expand into red giants, shedding their outer layers into space. What remains is a dense, hot ember, a white dwarf. This remnant no longer produces energy. It simply radiates its residual heat very, very slowly. A white dwarf can cool for billions of years, progressively dimming until it becomes an invisible black dwarf. However, the universe is not yet old enough for even a single such object to have fully formed. Every white dwarf ever created is still glowing somewhere, quietly fading into obscurity. The stellar death of these objects is less of a supernova salute and more of a lingering coal, slowly cooling across cosmic timescales. Time near a black hole progresses slower than it does on Earth. In Einstein's theory of general relativity, gravity does not merely pull on matter, it warps spacetime itself. The stronger the gravitational field, the slower time flows when compared to regions of weaker gravity. Adjacent to a black hole where gravity is extreme, this effect becomes truly dramatic. If you were to orbit just outside the event horizon, time would pass significantly slower for you than for a distant observer. Minutes near a black hole could signify years elsewhere. This is not science fiction. It is a truly measurable effect, gravitational time dilation. We have observed it even in its milder form using GPS systems and satellites. Near black holes, this effect becomes profound. They slow down not just light, but they stretch time itself. The vacuum between galaxies is colder than any laboratory on Earth. Distant from stars, planets, and even gas clouds, the enormous intergalactic spaces are startling in their frigidity. The temperature there drops to a few degrees above absolute zero, approximately 207 Kelvin. This is colder than any natural location on Earth and colder than most conditions we can generate even in advanced laboratories. This extreme cold arises from the nearly complete absence of particles and energy. There is nothing present to retain heat, only rare atoms and the faint microwave glow of the early universe. These intergalactic voids are the quietest and most solitary places we know. Vast and empty, stretched across millions of light years, they represent the deepest shadows of the universe, preserving only the background whisper of creation. The universe grows increasingly transparent as it ages. In the early universe, light could not travel freely. Space was filled with a hot plasma, a fog of electrons and nuclei that constantly scattered photons. However, as the universe expanded and cooled, it reached a critical moment when electrons combined with nuclei, forming neutral atoms. Suddenly, light was able to move unimpeded. This event, known as recombination, occurred approximately 380,000 years after the Big Bang and released the cosmic microwave background radiation that we observe today. Since that time, the universe has continued to become more transparent. The formation of galaxies and stars added new light sources, and as matter disperses, fewer and fewer objects obstruct a photon's path. Over time, the darkness became clearer. Space that was once glowing and opaque now presents virtually no barrier to light. We have captured the shadow of a black hole. In 2019, the Event Horizon Telescope presented the first direct image of a black hole, or more precisely, its shadow. The black hole itself is impossible to see, but the luminous ring of superheated gas surrounding it betrays its presence. This black hole is located at the center of the M87 galaxy, approximately 53 million light-years away from us. The image displays a circular shadow, an area from which light cannot escape, encompassed by a halo of radiation warped by gravity. The creation of this image required years of global collaboration. Telescopes across the world combined their capabilities to form a single planet-sized instrument. The result was more than just a picture, it was a quiet scientific triumph. Our first glimpse of one of the universe's most enigmatic objects. Not through fiction or theory, but through light. You can see a galaxy with the unaided eye right from your own yard. Most galaxies are so distant that even powerful telescopes render them merely as faint smudges. But there is one that can be observed without equipment, the Andromeda Galaxy. On clear, dark nights in the northern hemisphere, it appears as a soft, hazy oval patch, barely discernible to the naked eye. It is located more than 2.5 million light-years from us, meaning the light you observe began its journey long before the appearance of humans. Andromeda contains 1 trillion stars, more than the Milky Way, and is slowly moving toward us. It is difficult to comprehend, yet you can simply look up and see an entire galaxy. Without a telescope, without filters, just the sky, your eyes, and the gentle glow of something immense and ancient drifting in the darkness. A tiny detector captured the whisper of a distant black hole collision. In 2015, the small observatory LIGO detected something incredible, a faint ripple in spacetime that originated more than 1 billion light-years away. It was caused by the collision of 2 black holes, which sent gravitational waves propagating through the cosmos. These waves are incredibly subtle. When they reach Earth, they stretch and compress space by less than the width of a proton. But with delicate instruments, we are capable of catching them. LIGO and its partner observatories function as cosmic hearing, listening for the deepest vibrations of the universe. This confirmed Einstein's prediction made a century earlier that massive events could generate waves even in the silence of space. We can sense a singular chirp from the merger of invisible giants, captured by a small detector in a quiet corner of a small blue planet. Certain regions of the universe are receding from us forever. The universe is expanding, and this expansion is accelerating. Space itself is stretching ever faster. Some galaxies are being carried away at such speeds that their light will never reach us. Even if we waited eternally, the space between us would grow faster than light could traverse it. They have already crossed the point of no return, moving beyond the cosmic event horizon. Over time, more parts of the universe will disappear from view. Not because they vanish, but simply because their light can no longer reach us. This is not what we notice in everyday life. But billions of years from now, the observable universe will shrink. The cosmos is not only growing, it is quietly letting go. Some black holes may be primordial, born before the first stars. Most black holes form following the collapse of massive stars. But there is another possibility: black holes that appeared during the very first moments of the universe, before stars emerged. These are called primordial black holes. They might have arisen from tiny fluctuations in the hot, dense conditions immediately following the Big Bang, regions where gravity compressed matter into supercompact knots. Some of them could have been minuscule, others growing over time. We have never detected them directly, but if they exist, they could explain dark matter, aid in galaxy formation, or shed light on the early history of the cosmos. They are older than the stars, older than the galaxies, silent fossils from the first seconds after the birth of time. Entangled particles can link distant corners of the cosmos. Quantum entanglement is one of the strangest effects in physics. When two particles are entangled, their properties remain correlated regardless of the distance between them. Change one and the other changes instantaneously, even across the abyss of space. This does not transmit information faster than light, but it hints at something. At the quantum level, reality is profoundly interconnected. Some physicists believe entanglement may be involved in the structure of space-time itself, perhaps even helping to maintain its integrity. Theoretically, particles that originated in the early universe could remain entangled today, stretched across the expanding cosmos. If this is the case, quiet, invisible threads may exist in space, connecting distant regions. Quantum echoes from the dawn of time, still persistent in the void between galaxies. The vacuum possesses quantum pressure. Even in perfectly empty space, devoid of atoms, particles, or radiation, energy persists. Quantum physics posits that a vacuum is never truly empty. It is a sea of tiny fluctuations. Particles and antiparticles spontaneously appear and annihilate. Fields gently fluctuate, constantly in motion. This activity creates pressure, vacuum energy. On large scales, it may account for dark energy, the force accelerating the expansion of the universe. Unlike other forms of energy, vacuum energy does not dilute as space grows. It remains constant, and the more space emerges, the faster it continues to stretch. A strange thought: the more nothingness there is, the more of something appears. The quiet power of the void may be precisely what is pushing the cosmos apart. Black holes emit faint heat over trillions of years. They are known for their darkness, so dense that not even light can escape. But thanks to the work of Stephen Hawking, we know they are not absolutely silent. According to quantum theory, black holes radiate faint heat, Hawking radiation. This arises at the boundary of the event horizon, where virtual particles sometimes split, allowing one to escape outward while the other falls inward. The escaping particle becomes real. This constitutes a small energy loss for the black hole. Over unimaginable timescales, this leakage causes the black hole to shrink and eventually evaporate. For a solar mass black hole, this process would take a trillion years. The quietest finale is not an explosion, but a slow dissolution into nothingness. There is more plasma in the universe than solid matter. When we think of matter, we typically picture solids, liquids, and gases. Yet, its most prevalent form is plasma. This is an ionized gas where electrons and nuclei move freely. Plasma fills stars, solar wind, interstellar space, and even the intergalactic medium. The vast majority of visible matter in the universe is, in fact, plasma. It behaves differently from other states, reacting to magnetic fields, flowing like a fluid, and transporting electric currents across immense distances. On Earth, we seldom observe it, in lightning, fire, or neon illumination. But in space, it glows ubiquitously, moves, and shapes what we observe, even if we do not always fully perceive its influence. Gravitational waves propagate at the speed of light. Gravity does not merely attract, it can oscillate. When massive objects, such as black holes or neutron stars collide, they transmit waves through spacetime. These waves stretch and compress space as they propagate in all directions. And they travel at the speed of light, the maximum possible velocity within the universe. Decades were required to develop instruments sensitive enough to detect them. Now we are capable of listening to these faint cosmic tremors. Each wave carries information about distant catastrophes, including the mass, spin, and degree of space-time curvature. Gravitational waves are silent to the ear, yet they are real, measurable, and remarkably subtle, barely perceptible whispers of the cosmos's structure. The cosmic web connects galaxies throughout the entire universe. If we could map galaxies on a gigantic scale, a pattern would emerge, a network of filaments and voids, the cosmic web. Galaxies are not scattered chaotically. They accumulate along invisible filaments of dark matter and gas that stretch between clusters. At the intersection points of these filaments, superclusters form, serving as nodes containing numerous galaxies. Between them lie immense, quiescent voids. The web is not directly visible, but becomes apparent in large-scale sky surveys. It resembles a lattice, a porous structure, or even the branching of neurons. This is structure at its largest scale, not random, but intertwined, as if organically grown. The James Webb Telescope observes galaxies that may no longer exist. Its objective is to look farther than ever before, which fundamentally means looking deeper into time. Light from distant galaxies travels to us for billions of years, and consequently, we observe them as they were in the remote past. Some of the galaxies observed by Webb may have already merged, faded, or completely transformed. Yet, their light is still en route, a frozen frame traversing the cosmos across epochs. This represents a peculiar characteristic of astronomy. Telescopes do not show us now, but rather a multitude of different thens, scattered throughout the history of the universe. Every deep field image functions as a time machine, a gallery of vanished light. Distant galaxies shine with light emitted before the Earth's formation. When viewing a galaxy billions of light-years away, we perceive not merely distance but age. This light commenced its journey long before the advent of Earth, prior to the Sun's formation, and well before the birth of our solar system. Some galaxies we observe emitted their light more than 10 billion years ago. It traversed the expanding space, stretching and shifting before finally reaching us. We are observing the deep past in real time. The stars we detect within these galaxies may have long since perished. Their light is a subtle reminder that the night sky holds narratives older than existence itself. Entire galaxies can vanish behind dust clouds. Even such giants can remain concealed. In certain regions of space, dense dust clouds obstruct the light originating behind them. This is dust, but not the household variety. These are minuscule particles of carbon and silicates floating in cold interstellar clouds. If a galaxy lies beyond such a cloud, most of its visible light is blocked. We can only detect it in the infrared, radio, or X-ray spectrum, which penetrates the dust more easily. This is how astronomers have discovered entire galaxies hiding in regions previously thought to be void. In space, darkness does not always signify absence. Sometimes it signifies anticipation. Some galaxies are encircled by perfect rings of distorted light. Occasionally, the gravity of one foreground galaxy bends the light emanating from another, more distant one. With perfect alignment, the effect known as an Einstein ring occurs. This is a form of gravitational lensing. The mass of the foreground galaxy warps space-time and acts as a lens for the distant light source. Einstein rings are rare but spectacular luminous circles created not by motion but by perspective and gravity. Their light may originate from a distant galaxy, a quasar, or even a supernova. These rings assist in measuring galactic masses, mapping dark matter, and determining the structure of the early cosmos. They are silent, flawless illusions created by the very geometry of space. Perhaps the universe is infinite. Gazing at the stars, we ask ourselves, where is the boundary? But observations suggest there may be no boundary. We only observe a limited region, the observable universe. But beyond its confines, space likely continues without end. There is neither an edge nor a center, just more galaxies, more distance, and more space. If this hypothesis holds true, the vast majority of the universe will always remain inaccessible. We will never be able to observe everything. An infinite universe implies not infinite possibilities, but infinite extent, tranquil and serene. Cosmic rays strike the Earth from the depths of space. Every moment, high-energy particles, cosmic rays, reach our planet. Some originate from the Sun, others from distant regions within the galaxy or even beyond. These are protons, atomic nuclei, and other fragments of matter accelerated by stellar explosions, black holes, or unknown forces. Most are deflected by Earth's magnetic field or absorbed by the atmosphere, but some reach the surface and a few pass straight through us. They are safe in small quantities, but serve as a reminder: space is not empty, it is filled with motion, energy, and invisible messengers of distant events. Occasionally, a single ray reaches a detector, delivering a history that began light years away, the journey of a particle from a supernova to our sky. Perhaps the concept of "before the Big Bang" does not exist. The phrase sounds intuitive but may be meaningless. According to general relativity and many models of cosmology, time commenced simultaneously with the Big Bang. It marked not only the birth of matter and energy, but also the inception of space and time itself. To ask what came before is analogous to asking what lies north of the North Pole. Some theories propose predecessor states or cycles, while others suggest a quantum domain outside conventional time. But in most models, the pre-Big Bang era remains an inaccessible concept. The Big Bang was not an explosion in space, it was the genesis of space itself. Quasars were once mistaken for nearby stars. The first quasars appeared as faint points, almost indistinguishable from typical stars. However, their emitted light exhibited peculiar behavior. Their spectra were anomalous, and their luminosity varied inexplicably. It required years to establish that these were not stars, but distant galaxies hosting active galactic nuclei. A quasar is powered by a supermassive black hole around which a heated accretion disk orbits. It shines with incredible brilliance, sometimes exceeding the luminosity of the entire host galaxy. The light from the first discovered quasars traveled billions of years to reach us, yet they still appeared as tiny points. This initial misidentification led to one of the most profound discoveries in astronomy. Our local group of galaxies is currently falling into a hidden region. The Milky Way is not stationary. Together with Andromeda and numerous satellites, it moves as part of the local group. This group itself is streaming towards something larger, a gravitational anomaly known as the Great Attractor. Yet further away lies a more enigmatic domain, the Shapley supercluster, and potentially other massive structures concealed behind the dense plane of our galaxy. These immense configurations exert a gravitational pull on us, although we cannot view them completely. It is as if our entire cosmic neighborhood is slowly sliding towards something enormous, cloaked in shadow. We do not know precisely what is hidden in that direction, only that we are gradually migrating there, drawn by the gravity of unseen giants. We are living in the stellar spring of the universe. The cosmos is currently filled with stars that are forming, burning, and exploding, but this was not always the case. For the first hundreds of millions of years following the Big Bang, the universe remained dark. Not a single star existed. Only later did the first luminous objects emerge, illuminating the darkness and initiating the chain of cosmic evolution. Since that epoch, the rate of star formation increased, reached its peak, and has begun a slow decline. We inhabit what can be termed a cosmic spring, a period when new stars continue to appear, but already less frequently than before, and significantly more frequently than they will in the distant future. Eventually, the last star will be born, and subsequently, the universe will begin its gradual darkening. But for now, it remains full of new beginnings. It is luminous enough to inspire wonder and tranquil enough for repose. In the far future, stars will cease to be born. Their inception depends on cold gas, clouds of hydrogen and helium, which must collapse under gravitational force. But over time, this fuel reservoir will be depleted. It is locked within existing stars, dispersed by supernova explosions, or heated to useless temperatures. Billions of years from now, galaxies will lack the necessary material for new stellar objects. The remaining stars will age, burn out, and fade. First, the blue giants, then stars similar to the Sun, and finally the red dwarfs, until even the dimmest stellar sparks cool into absolute darkness. The end of the universe will not be sudden. It will arrive gradually, quietly, and gently. What will remain are black holes, white dwarfs, neutron stars, and the silence of a cooled cosmos. Not a tragedy, simply stillness. The majority of matter in the universe is invisible. When we observe the cosmos, the stars, galaxies, and nebula, we are seeing only a small fraction of what actually exists. Most of this matter does not radiate. It neither absorbs nor reflects light. This is dark matter. We have never observed it directly, but we know of its existence due to gravity. Galaxies rotate faster than expected. Light bends more severely than anticipated. Clusters cohere more tightly than their visible mass allows. All of this indicates a hidden substance. It constitutes more mass than ordinary baryonic matter. Dark matter permeates everything, forming the large-scale structure of the cosmos. We simply cannot observe it. It is the quiet, invisible scaffolding holding the world together. The light from the first galaxies is stretched by the expansion of the universe. When light traverses space, it does not merely travel, it is stretched, because the universe itself is expanding and pulls the light waves along with it. Light that departed the earliest galaxies billions of years ago has lengthened, shifting from the visible spectrum into the infrared. This phenomenon is called cosmological redshift, and astronomers use it to measure distance and time. The more severely stretched the light, the more distant and ancient the source. With telescopes like the James Webb Space Telescope, we are finally observing this archaic light, faint and reddened by its journey. What was once the radiance of young stars reaches us now as a whisper, stretched by the very breath of spacetime. The universe might be a hologram. This sounds fantastical, but some physicists seriously consider the possibility that our three-dimensional world is merely a projection of a deeper, two-dimensional reality. This is known as the holographic principle. It originated from black hole research, where all information regarding matter falling into them appears to be encoded on the surface area rather than within the volume. Some theories propose that the entire universe may function similarly. What we perceive as spatial volume and depth could be a mathematical illusion generated from data stored on a distant boundary. This has not been proven and does not affect daily life, but it serves as a subtle reminder. Reality, even in its most robust form, might be different from how it appears. Space-time may be grainy at the smallest scales. To the naked eye, and even under a microscope, space appears smooth, continuous, and empty. However, certain theories of quantum gravity suggest that space is composed of tiny elemental units like pixels. This minimal scale is called the Planck length, approximately 10 to the minus 35 meters. At this level, smoothness may break down into something more fundamental, a foamy structure of space-time itself. We do not yet possess the instruments necessary to observe or even verify this hypothesis. But if it proves true, then everything, the stars, thoughts, and dreams, occurs not in a void, but within a universe where structure exists at every single level. There are stars that spin faster than kitchen blenders. Some stars rotate so rapidly that their equators bulge, and their surfaces transform into a blurred rim. Neutron stars take this to an extreme. Millisecond pulsars rotate hundreds of times per second. This means that an entire star, city-sized and possessing the density of an atomic nucleus, rotates faster than the blades of a blender. They emit narrow, collimated beams of radiation that sweep across space like cosmic lighthouses and pulse with remarkable precision. Many of them orbit binary companions, accreting their matter and accelerating their spin rate. They are among the most rapid objects in the cosmos and some of the most accurate clocks. Silent, fast, unchanging. The universe may end in a quiet, slow fading away. Scientists once hypothesized that the cosmos would eventually collapse again, but current data indicate otherwise: eternal expansion. Galaxies will recede further, star formation will become rarer, and the night will grow darker. Some stars will fade, then others. Black holes will evaporate, matter will decay, and the universe will become cold, silent, and nearly void. This state is referred to as heat death. It is not a sudden conclusion, but a gentle dissolution. Over trillions of years, energy will dissipate, structures will vanish, and the cosmos will become static. Not an end of fire or ice, but an end defined by silence. The universe, which once whispered itself into existence, will depart just as quietly. Some galaxies exhibit superwinds capable of carrying stars. Powerful outflows can blow from the cores of galaxies, especially those with active black holes or intense starburst activity. They expel gas, dust, and even young stars across tens of thousands of light years. These superwinds are driven by radiation pressure, magnetic fields, and supernova explosions. Over time, they can strip a galaxy of the gas required for new luminous objects, rendering it quiescent and red. However, they also disperse heavy elements throughout the cosmic web, preparing material for future stars and planetary systems. Thus, the galaxy breathes, inhaling matter, igniting it, and then releasing it. The distant future of the cosmos is an infinite, dark ocean. In trillions of years, the universe will be fundamentally different. Galaxies will have receded so far that each will appear as an island in the darkness. New stars will cease to form, old ones will fade. Even white dwarfs will cool, leaving behind cold remnants, black holes, and a faint trace of ancient light. And over incomprehensible timescales, black holes will evaporate, and all matter will eventually decay. Only isolated particles will remain, drifting in the void. This is the ultimate heat death, not an abrupt conclusion, but vast, dark stillness, a cosmic ocean without waves, wind, or shores. We might reside within a giant cosmic void. The universe is structured by clusters of galaxies separated by enormous empty regions known as voids. These extend for hundreds of millions of light years and contain very little matter. Some scientists propose that we may be situated inside such a void, a region less dense than the cosmic average. This could potentially explain some observations, the expansion rate of the universe, or the characteristics of the cosmic microwave background. Life inside a cosmic void is personally no different for us, but this implies that what appears to be emptiness is part of a larger pattern, the quiet center of a cosmic bubble drifting within a network of invisible gravity. Magnetars possess magnetic fields trillions of times stronger than Earth's. A magnetar is a neutron star, the dense remnant of a dead star compressed to the size of a city, exhibiting an incredible magnetic field strength. Earth's field is sufficient to deflect a compass needle. A magnetar's field is so powerful it can erase data thousands of kilometers away, distort atomic structure, or rip matter apart. These fields are short-lived, but while they exist, they generate flares and immense energy bursts. A single magnetar flare, even originating from the opposite side of the galaxy, can be detected on Earth. No terrestrial laboratory is capable of generating anything similar. They are among the most extreme objects in the universe, dense, silent, enveloped by an invisible force, like stars transformed into pure memory and magnetism. The largest known structure in the universe is the huge LQG, Large Quasar Group. In 2013, astronomers discovered an enormous structure composed of quasars, the bright nuclei of active galaxies, spanning over 4 billion light-years. This structure, known as the Large Quasar Group, is so immense that it challenges our understanding of cosmological homogeneity. According to theory, the cosmos should be relatively smooth on immense scales, lacking structures of this magnitude. However, this group exceeds the model's limits. It consists of dozens of quasars connected in a single pattern, which may indicate that the early universe formed larger structures than we had previously assumed. Perhaps it is a statistical anomaly, or perhaps a sign that the cosmos is more complex and interconnected than our models predict. Black holes can twist space into a time vortex. A black hole not only captures light, it warps space-time. Approaching the event horizon, one observes space becoming severely curved and time decelerating. For an external observer, time near the black hole nearly halts. This curvature generates a funnel-like structure, narrow, deep, and unidirectional. Inside, all paths converge toward the central singularity. The closer one gets, the more pronouncedly time and space appear to exchange roles, where the inward spatial direction is transformed into a temporal progression. Return is impossible. This warping is not a metaphor. It is the geometry dictated by gravity. Certain regions of the universe will never observe each other. Because the universe is expanding and accelerating, some of its components are already receding from one another faster than light can bridge the distance between them. This implies that even waiting infinitely, light from those regions will never reach us. Conversely, we can never transmit a signal to them. Over time, increasingly more regions will pass beyond the cosmic horizon of reachability. Each galaxy will essentially become an island, isolated by darkness. This does not violate the laws of physics. No object moves faster than the speed of light through space. Space itself is simply expanding with a tranquil, unstoppable motion, separating regions of the cosmos permanently. Gold is the most difficult element to synthesize in stellar explosions. Gold is rare on Earth, not just economically, but throughout the entire universe. It cannot be created within the core of a typical star. It emerges only during the most extreme events, such as the collision of neutron stars or specific types of supernova. In these moments, atomic nuclei collide under immense pressure and heat, synthesizing heavy elements: gold, platinum, uranium. These valuable atoms then disperse into space, mixing with gas clouds and becoming components of new stars, planets, and people. Every gold ring, every grain of dust is the residue of a cosmic catastrophe, a silent trace of ancient violence now resting on your hand. In this context, gold is not merely beautiful, it is ancient, stellar, forged by a universe that hammers its treasures in fire. The space between galaxies expands while light traverses it. When we observe light from distant galaxies, we see it as it was long ago, but also stretched by the space it has crossed. As the universe expands, the distance light must travel increases, meaning the light itself is stretched. Its wavelength increases, shifting toward the red end of the spectrum. This phenomenon is termed cosmological redshift. Light neither slows down nor loses energy due to collisions. Simply, the space through which it travels becomes larger. Essentially, the universe stretches the signal on its path toward us. Consequently, when we observe distant galaxies, we do not merely see age or distance. We observe how space has changed since that light began its journey, a quiet record of the universe's expansion. Fossilized sound waves are imprinted upon the structure of the cosmos. In the early universe, before the formation of atoms and the release of free light, matter and energy were tightly coupled within a hot plasma. Within this plasma, pressure and gravity generated oscillations, waves of compression and rarefaction, analogous to sound waves in air. These acoustic oscillations left an imprint on the density of matter, a fossilized echo. Today, this can be observed in the distribution of galaxies, a preferred spacing between galaxy pairs, resembling a standing wave preserved in space. This phenomenon is known as baryon acoustic oscillations, BAOs. It is subtle yet measurable, a fossil trace of cosmic sound that resonated before the universe became transparent. A wave that does not disappear, silently shaping everything we currently observe. Galaxies can completely vanish, absorbed by larger structures. On the scale of cosmic evolution, galaxies do not simply drift in isolation, they interact, collide, and sometimes assimilate one another. When a smaller galaxy approaches a massive one too closely, the latter's gravity can tidally disrupt it. Stars are stretched into long streams, entering the halo of the larger galaxy and eventually mixing thoroughly until the smaller system disappears. We have found traces of such mergers surrounding the Milky Way, manifesting as stellar streams tracing across the sky. This process is known as galactic cannibalism. However, it is not violent, it is slow and gradual. Over time, large galaxies grow in this manner, not by constructing but by quietly assimilating. One galaxy dissolves into another, leaving behind only a ripple of stars. There are stars that flicker like fireflies in the night. Not all stars shine steadily. Some pulsate, oscillate, or dim and reignite in rhythmic cycles. These variable stars change due to various mechanisms: internal pressure waves, surface flares, or occultation by orbiting companions. From Earth, they appear to gently blink, following a slow stellar cadence. For some, the cycle spans hours. For others, years. These variations are not random. Many are remarkably stable, operating as celestial clocks. Astronomers utilize them to gauge distance across the entire universe. A single repeating flicker can reveal how far away a star is, and how intrinsically luminous it is. Stars do not merely burn, some of them breathe. Some black holes wander in solitude. Not all black holes reside at galactic centers. Some are transients. A black hole can be ejected from its host galaxy via gravitational interactions, thrust out during a galactic collision, or repelled by the recoil from a merger. Once liberated, it becomes a vagrant, traveling through interstellar or even intergalactic space. Such black holes are difficult to detect. They are invisible unless they are passing through gas or significantly affecting nearby stars. Yet, they likely exist, drifting in the darkness, untethered and unlit. They possess no orbit, no companions, no home, only mass, momentum, and the gravity of matter that fell inward and never stopped falling. Even black holes can be propelled across a galaxy. When two black holes merge, the resulting burst of gravitational waves can be asymmetric. If energy is radiated preferentially in one direction, the newly formed black hole experiences a recoil, a gravitational kick, that can propel it away at speeds up to 1,000 kilometers per second. Some black holes may escape the boundaries of their galaxies to roam the intergalactic void. Others remain in vast, extended orbits. These displaced black holes are challenging to observe, but astronomers are confident they exist. Silent wanderers driven by the memory of their own collision. Even the heaviest, most robust objects in the universe can be displaced by the right wave. Some stars persist merely as exposed carbon cores. When a star like our Sun expires, it sheds its outer layers and leaves behind a core known as a white dwarf. Some white dwarfs are composed primarily of carbon, and under immense pressure, this carbon can crystallize. Stated differently, some stars transform into gigantic diamonds. These stellar diamonds are the size of Earth, yet far more massive, and faintly glow with residual heat. They no longer sustain nuclear reactions, but continue to shine for billions of years until they cool down into darkness. Astronomers have even detected pulsations in some white dwarfs akin to the ringing of a bell. A silent, cooling jewel in space. Once a star, now a crystal of ancient fire. The vast majority of the universe's history still lies ahead. 13.8 billion years sounds like an immense duration, but if we consider the entire future of the universe, not tomorrow, nor even a million years from now, but trillions of years, we are still at the very beginning. Stars continue to be born, galaxies continue to assemble. Black holes still glow with the heat of infalling matter. In the distant future, stars will extinguish, galaxies will disperse, and the universe will become cold and silent. But that chapter has yet to begin. Currently, we are living in a moment of light, a brief golden era when the cosmos is full of motion and change. The past is vast, but the future is even greater. Supernova remnants continue to expand for thousands of years. When a massive star dies, it explodes as a supernova, a blinding flash that can briefly outshine an entire galaxy. However, the event does not conclude with the flash. The shock wave expands for centuries, even millennia, sweeping up gas, dust, and everything in its path. These expanding shells are called supernova remnants. They glow across many wavelengths, radio, X-ray, and visible light, and their structures reveal the history of the explosion. Some form delicate filaments, others turbulent clouds. The Crab Nebula, one such remnant, is still expanding after the explosion witnessed on Earth in 154. Supernova remnants are the slow exhalations of dead stars, persisting long after the flash fades. The light of a distant star can be bent by a simple planet. We usually think of gravitational lensing as something performed by stars, black holes, or galaxies. But even a planet is capable of this. If a planet passes exactly between a distant star and Earth, it acts as a tiny lens, slightly amplifying and distorting the light. This is called microlensing. It is subtle and rare, yet strong enough to detect planets that would otherwise be impossible to see, even in other galaxies. A tiny flicker, a slight arc of brightness, and before us is a new world. The planet may be cold, dark, and invisible, but it slightly warps the light, and that is enough for it to say, "I exist." The universe once glowed with a bright orange light. In the earliest days after the Big Bang, it was a hot, dense plasma radiating intense light. But as it expanded and cooled, the glow changed. When the temperature dropped to approximately 3000 Kelvin, the first atoms formed, and light was able to propagate freely. At this moment, the entire universe would have appeared orange, not like a dark sky, but as a soft, warm radiance filling all space. This light has been stretched by the expansion of the universe into microwave radiation, the cosmic microwave background. But a long time ago, the entire cosmos glowed orange, like a quietly burning coal. Heat. Certain regions of the universe cool more slowly than others. As the universe expands, it cools gradually and gently, like an immense oven that has been switched off. However, not all domains cool uniformly. Regions possessing a greater density of matter or trapped radiation retain thermal energy longer. A galaxy cluster, for instance, holds hot gas that remains warm for billions of years. Other regions are emptier or more void and cool more rapidly. These thermal anisotropies influence the formation of structures, stellar evolution, and the duration of cosmological processes. Even within this seemingly simple cosmos, there are localized nuances, warmer pockets, areas of slow decay, minor lags in the great unfolding. The universe does not cool like a machine. It cools like weather, unevenly, texturally, and quietly alive. Someday we might observe the birth of a new universe. Certain cosmological theories postulate that new universes could emerge within hours through quantum fluctuations, black holes, or other currently unknown mechanisms. If this occurs, it happens far from us, outside our observational horizon. But theoretically, one might detect signatures, a suddenly expanding bubble of new physics separating from our localized reality. We do not know if this has ever transpired, nor if it will occur. Yet the idea remains that one day the quiet darkness of our cosmos may give rise to something new, a beginning within an ending, a whisper within the silence. The cosmos still resonates from its initial moments. In the first fractions of a second following the Big Bang, the universe underwent explosive expansion, the inflationary epoch. This surge of motion left ripples, minute quantum fluctuations stretched by spacetime. These became the seeds of all subsequent structures, galaxies, stars, planets, and left behind an echo. We perceive this echo in the cosmic microwave background, CMB, as temperature anisotropies, and we may one day detect it as primordial gravitational waves, faint rhythms in the fabric of spacetime. The universe appears silent, but within it, the memory of the initial impulse still rings, like a bell that continues to vibrate long after being struck. The universe is immense, and you are a mechanism for it to comprehend itself. Among all the strange facts of astrophysics, this is the most quietly astonishing. You are constructed of stardust. The carbon in your body, the calcium in your bones, the iron in your blood, all were forged within stars, dispersed across the cosmos, and assembled into life. You are not separate from the cosmos. You are a moment of the cosmos that has attained consciousness, a spark of awareness in a universe that otherwise only moves, burns, and cools. In this sense, the universe has gained eyes, and through those eyes it observes itself, marvels at itself, and dreams of itself. And even now, as you slowly drift toward sleep, it continues to dream. Thank you for spending this time here. Drifting through the cosmos with me, we traversed incredible distances, flew past dying stars and newly formed galaxies and listened to the ripples in? And somewhere amid all this, in the light of ancient stars, in the silence between galaxies, in the quiet shimmer of cosmic dust, you existed, slowly breathing, thoughts softening, perhaps already bordering on sleep. This universe is filled with dynamic motion and profound mysteries, yet within it there also resides a palpable stillness. It contains thermal energy, photons, and gravitational influence. Simultaneously, it holds profound silence. And the fact that we are able to comprehend its tranquility, progression by progression, world by world, calmly and quietly, is genuinely beautiful. Therefore, wherever you may currently be, awake or already drifting past the threshold of consciousness, may your dreams tonight be gentle. May your physical form rest, much like starlight resting upon a fluid surface. And may there remain with you even a faintly discernible memory of the universe, which illuminates not only above you, but also intrinsically within you. If you remain awake, you may proceed to the subsequent chapter immediately. However, if the desire is to delve into further narratives, quietly conveyed and rich with wonders, consider a subscription. There is always more to investigate, one quiescent mind at a time. Good night.